Hi. First, I wanted to talk about the steps of a one-sample t-test, and I also wanted to talk some about the sampling distribution of a one-sample t-test. Right here it says that the purpose of a one-sample t-test is to test if the mean of a population, such as a population of people, equals a certain value. This could be an example of a one-sample t-test. A person wants to test if the mean IQ of college students living in the US equals 100. The person has to collect a data set in order before they can test whether this is the average IQ in the US. Let's look at what the data collection of a one-sample t-test involves. It involves selecting a sample from the population that you're interested in and collecting a data value from each member of the sample. And also, it involves calculating the mean of your sample. So this person, in my example, has recorded the IQs of a sample of 100 recruited college students, and those 100 recruited college students who provided their IQ scores had a mean IQ of 130 with a standard deviation of 10. So we have our data set, but how do we know what decision to make about whether the mean IQ of college students in the US equals 100? There's two possibilities that might be true. Either the mean does equal 100 or it doesn't equal 100. Regardless of whether we decide or think that regardless of whether we think it equals 100, it either does equal 100 or doesn't equal 100. In reality, only one of those two things can be true. And the two possibilities of what might be true are the null hypothesis and the alternative hypothesis. The null hypothesis. First, let's talk about the null hypothesis. It says the population mean equals 100, meaning the mean IQ of the college students living in the US does equal 100. The null hypothesis just says that the mean of the population that we're interested in does equal the value that we're testing. And when we do this one-sample t-test on our data set, we're using it to make a decision about whether this null hypothesis should be rejected. We're wondering whether we should reject the possibility that the mean IQ equals 100. And how is this decision made? Well, you have to have a test statistic to make that decision. Let's look at the test statistic of a one-sample t-test. On the top of the formula, right here, it's the sample mean, the mean of the sample that was the data was collected from, minus the population mean being tested, over the standard deviation of the sample that was selected, and the size of the over the square root of the size of the sample that was collected. So let's see if we can calculate that t-score, which is the test statistic in a t-test is a t-score. That's why it's called a t-test, actually. And in another type of test, like an f-test, the test statistic would be an f-score. So we're going to subtract our sample mean of 130 by the population mean that we're testing, which is 100. And we're going to, on the bottom, we have the standard deviation of our sample, which is 10, over the square root of our sample size. We recruited 100 college students to be in our sample. top will end up being 30. The bottom is 10 divided by the square root of 100. The square root of 100 is 10, so it's 10 divided by 10, which comes out to 1. It comes out to 30, which is a large t-score. The only thing we really have to check is whether this t-score reaches the critical value. If the t-score, which is the test statistic, is at the critical value or higher, we reject the possibility that the mean IQ of college students in the US is 100. If the t-score comes out below the critical value, we simply don't reject this claim right here, and we actually just remain uncertain about whether it equals 100. In a hypothesis test, you can either reject the null hypothesis and claim that it appears to be wrong, or you simply can't reject it and you're stuck not being sure whether the null is true or false, and you just continue to give the null hypothesis the benefit of the doubt and assume it's true, but you haven't really, if you can't reject it, then you haven't really shown evidence for it or against it. You can't really make a firm conclusion in that case, either way. Sometimes people will think that if you reject the null hypothesis, it means you're saying that the null hypothesis appears to be wrong, which is true. If you reject the null hypothesis, it does mean you're saying that the null appears to be wrong. But people sometimes think that if you fail to reject it, it means you're saying that the null appears to be true, which isn't really the case because you can't really support a null hypothesis. You can either reject it or not reject it. The test is designed in a way where it can either reject the null hypothesis or it simply can't reject it. How can we find out what our critical value equals? In order to get our critical value, we need the DF, degrees of freedom. Let's see what the DF is of a one-sample t-test. It's n minus 1, which is just the number of people in the sample minus 1. We recruited 100 students, so it's 100 minus 1, which is 99. That's our DF. And now we can go to a critical value table that I'll show you how to use. This is going to be the critical value table for a t-test. See if I have it on my desktop. I guess not. I need to zoom it in so it's covering the whole screen. I think this is the one I want. Okay. No, I think I can find a better one. Okay. Our DF was 99. Let's see if that actually shows up on here. We'll have to use 99 it's not showing up, which means we have to actually use the next lower one, which is 80. If it had 99, we would want to use 99, but since it's not there, we have to use 80. This says one tail or two tails. We have to decide which of these two types of tests we're doing, a one-tailed test or a two-tailed test. And I'll show you why that's important. All of the possible samples of 100 that might have been selected from this population of all college students in the US has its own t-score. So here's one sample of 100. Here's another sample of 100. There's actually many more combinations of 100 that could be selected than what I'm showing on here. If you wanted to know how many combinations of 100 there are, you could use that combinations calculator that I showed you. Let's see. These are all, there's 100 people inside each of these. And there's a curve going around that outlines all of these combinations. And the curve that outlines the combinations in this case is a t-distribution curve. The t-distribution is the curve that outlines the samples that are stacked above their t-scores in this histogram right here. It's basically the shape of the t-scores of all of the possible samples. And the shape of the t-distribution curve actually depends on degrees of freedom. All of these possible samples have 100 people inside of them, which means each one of these boxes has a degrees of freedom of 99, just like our combination of 100 does. So this exact shape that outlines our samples is actually a t-distribution with degrees of freedom of 99. There's actually different, a t-distribution actually isn't just one shape. It's actually a category of shapes. And the exact shape of it actually depends on what the degrees of freedom are, because when the degrees of freedom is higher, you have the t-distribution curve will be more bell-shaped. And when the degrees of freedom are low, the t-distribution is flatter and thicker in the tails than a bell curve. even though it's still symmetric. Now let's look at where the critical values are. First, let's start with a one-tailed test. In a one-tailed test, the critical value is actually the point on this t-score number line. It's the t-score that will have 5% of the possible samples to the right of it or above it, meaning the critical value is the point that has, it's the t-score that that's the point at which 5% of the possible samples will have t-scores either at this point or above it, with higher t-scores up here. So this area is 5%. And here you have a critical value right here. And you can also have a critical value at the left end right here. And this point is actually the t-score that has 5% of the possible samples either at that point or to the left of it with lower t-scores. And the middle of the t-score number line is at 0. And this point right here is actually called a positive. This would actually be a positive critical value. And this one down here would be a negative critical value because it's a negative number. It's below 0. Positive critical value and negative critical value. And we can actually find out what the positive and negative critical values are. For our example right here, we need our degrees of freedom, and we need to know that we're doing a one-tailed test. And now we can go to our table. I said we're using 80 because 99 isn't there. We have a one-tailed test because we're using the critical value with 5% beyond it. And so we go to one tail, we go to 0.05, and then we go down to 88. The reason we're using 0.05 is because each of these critical values has 5% beyond it. There's a 5% piece down here and a 5% piece at the upper end. Let's go down to 88. I mean 80. What do we end up with? 0.05. The second column. About 1.66 for our critical value, and the negative critical value will actually be the number that's just the opposite of what we found in the table. And in a one-tailed test, a person can actually only use one of these two critical values in a one-tailed test. A person in a one-tailed test, a person will have to predict which side of the curve their outcome is going to end up at. And we'll talk about this more later. A positive t-score, like ours, has to be compared to the positive critical value, which means if you get a positive t-score, you have to check to see if it's above this point in this area up here, because you can't compare our positive t-score to this negative critical value. If you get a negative t-score, you have to compare it to this negative critical value and see if you're in this area down here. In a one-tailed test, a person, before the study is done, before the data is collected, the person actually predicts whether, or at least has an idea about whether they're going to end up with a positive t-score or a negative t-score. And based on whether they think the t-score will be positive or negative, they choose which critical value that they're planning to use ahead of time. If the person thinks that the t-score will be positive, the person selects the positive critical value, and if the person continues to do a one-tailed test, the person has to use this positive critical value that they chose ahead of time. And if they end up getting a negative t-score, they actually can't do the one-tailed test that they were planning to do, because they're only allowed to use this positive critical value that they plan to use ahead of time. If the person thinks that the t-score will end up being negative in their data set, ahead of time they select the negative critical value and they plan to compare their value to the negative critical value. And if it ends up being a positive t-score, they're stuck, and they don't have a critical value to compare it to. So in a one-tailed test, you have to commit yourself to using one of the two critical values, because in a one-tailed test, basically you're only allowed to use one critical value. If you're planning to use the positive critical value, then you reject the null hypothesis if you end up in this area up here, beyond the critical value. If you're planning to use the negative critical value, you check to see if your score is in this negative area. And if it ends up down here, you reject the null hypothesis. What if it's a two-tailed test? You still have your curve of possible samples. Above their t-scores. And we would still have this t-distribution curve. In a two-tailed test, the difference is the critical values actually only have 2.5% beyond them. Only 2% of the combinations are in these areas up here that's beyond the critical value. let's see. This one down here is also 2.5%. And then this area down here with these outcomes, or these combinations, is actually called a rejection region. The rejection region is the area beyond the critical values. Actually, it's the area at the critical value or beyond the critical value. And in a two-tailed test, the person who's doing the study doesn't commit themselves to only one critical value. What the person does is the person waits. The person simply waits to see if their t-score is positive or negative. If it ends up being a negative t-score, they compare it to the negative critical value. If it's a positive t-score, they compare it to the positive critical value. And so you can think of rejecting the null hypothesis as sort of like scoring a goal in the goal area of a field. And if you end up selecting a combination of people that's at the critical value or beyond the critical value, you can reject the null hypothesis. But in a one-tailed test, you're committing yourself to one critical value ahead of time, which basically means you can only reject in one goal area. If you commit yourself to the positive critical value, you can only reject if you make it up into this area. You're not allowed to reject down in this area. If you commit yourself to using the negative critical value, you have to reject in this area. This is your only goal area, because you're not allowed to score you're not allowed to reject the null hypothesis down here, because you're not allowed to use this critical value. You're not allowed to compare your number to this critical value. But in a two-tailed test, you're allowed to either reject the null hypothesis down here or up here. So and I'm going to stop this video for a second, and I'll start it up again.